subset sums and knapsacks adding a variable, we're seeing more and more that issues in scheduling provide a rich source of practically motivated algorithmic problems. So far, we've considered problems in which requests are specified by a given interval of time on a resource, as well as problems in which requests have a duration and a deadline but do not mandate a particular interval during which they need to be done. In this section, we consider a version of a second type of problem with durations at deadlines, which is difficult to solve directly using the techniques we've seen so far. We will use dynamic programming to solve the problem, but with a twist. The obvious set of subproblems will turn out not to be enough, and so we end up creating a richer collection of subproblems. As we will see, this is done by adding a new variable to the recurrence underlying the dynamic program. The problem. In the scheduling problem we consider here, we have a single machine that can process jobs, and we have a set of requests that set 1 to 3 until n. We are only able to use this resource for the period between time 0 and time w for some number w. Each request corresponds to a job that requires time wi to process. If our goal is to process jobs so as to keep the machines as busy as possible up to the cutoff w, which jobs should we choose? More formally, we are given n items, the set 1 to 3 until n, and each has a given non-negative weight wi for I equals to 1 to 3 until n. We are also given about w. We would like to select a subset S of the items so that the summations of wi, summing for all I in S, is less than or equal to w, and subject to this restriction, the summations of wi, summing for all I in S, is as large as possible. We will call this the subset sum problem. This problem is a natural special case of a more general problem called the knapsack problem, where each request I has both a value vi and a weight wi. Request I has both a value wi more general problem a way to select a subset of a maximum total value subject to the restriction that its total weight not exceed w. Knapsack problems often show up as subproblems in other, more complex problems. The name knapsack refers to the problem of filling a knapsack of capacity w as full as possible, or packing in as much value as possible, using a subset of the items 1 to 3 until n, such a set. We will use weight or time when referring to the quantities wi and w. Since this resembles other scheduling problems we've seen so far before, it's natural to ask whether a greedy algorithm can find the optimal solution. It appears that the answer is no. At least no efficient greedy rule is known that always constructs an optimal solution. One natural greedy approach to try would be to sort the items by decreasing weight, or at least to do this for all items of weight at most w, and then start selecting items in this order as long as the total weight remains below w. But if w is a multiple of 2 and we have 3 items with weights among the set w over 2 plus 1 and w over 2 and w over 2, then we see that this greedy algorithm will not produce the optimal solution. Alternatively, we could sort by increasing weight and then do the same thing, but this fails on inputs like 1, w over 2, and w over 2. So the goal of this section is to show how to use dynamic programming to solve this problem. Recall the main principles of dynamic programming. We have to come up with a small number of subproblems so that each subproblem can be solved easily from smaller subproblems, and the solution to the original problem can be obtained easily once we know the solutions to all the subproblems. The tricky issue here lies in figuring out a good set of subproblems. Designing the algorithm, a false start. One general strategy, which worked for us in the case of weighted interval scheduling, is to consider subproblems involving only the first I request. We started by trying this strategy here, we use the notation OPT of I, analogously to the notation used before to denote the best possible solution using a subset of the request among the set 1 to 3 until I. The key to our method for the weighted interval scheduling problem was to concentrate on an optimal solution O to our problem and consider two cases, depending on whether or not the last request N is accepted or rejected by this optimal solution. Just as in that case, we have the first part, which follows immediately from the definition of OPT of I. If N is not in O, then OPT of N is equals to OPT of N minus 1, because we do not choose N. Next, we have to consider the case in which N is in O. What we like here is a simple recursion, which tells us the best possible value we can get for solutions that contain the last request N. For weighted interval scheduling, this was easy as we could simply delete each request that conflicted with the request N. In the current problem, this is not so simple. Accepting request N does not immediately imply that we have to reject any other request. Instead, it means that for the subset of requests S, which is a subset equals to the set 1 to 3 until n minus 1 that we will accept, we have last variable weight left. A weight of Wn is used on the accepted request N, and we only have W minus Wn weight left for the set S of remaining requests that we accept. So we see the figure 6.10. A better solution. This suggests that we need more subproblems. To find out the value for OPT of N, we not only need the value of OPT of N minus 1, but we also need to know the best solution we can get using a subset of the first N minus 1 items and the total allowed weight W minus Wn. We are therefore going to use many more subproblems, one for each initial set among the set 1 to 3 until I of the items, and each possible value for the remaining available weight W. Assume that W is an integer
the available weight W is
equals
we call
to
little
1 to
w.
n have
Assume that
weights Wi.
capital W,
We
big
will have
W,
a subproblem
an
for
integer,
each I equals
and
to
all
0, 1
requests
to 3
I
until
equals to
n,
1 to 3 until
integer
n
0, which is
have
less than
integer
equals
weights
to
Wi.
W. We will have a
Little
subproblem
w,
for
which
each
is
I
also
equals
less
to
than
0, 1 to 3 until n,
big
and
W.
each integer 0, which is less than equals to little w, the remaining available weight, which is less than equals to W, the integer. We will use OPT of IW, little w, to denote the value of the optimal solution using a subset of the items 1 to 3 until I, chosen among 1 to 3 until I, with a maximum allowed weight W. That is, OPT of IW is equals to the maxima of the summations of Wj, summing for all index j in S, where the maxima is taken among all possible S. And where the maxima is over the subset S, which is subset equals to the set 1 to 3 until I, that satisfies the summations of Wj summing for all j in S, which is less than equals to little w. Using this new set of subproblems, we will be able to express the value OPT of IW as a simple expression in terms of values from smaller problems. Moreover, OPT of NW is the quantity we're looking for in the end. As before, let O denote the optimal solution for the original problem. If N is not equals to O, not in O, then OPT of NW is equals to OPT of N minus 1 W, since we can simply ignore item N. If N is in O, then OPT of NW is equals to Wn plus OPT of N minus 1 and W minus Wn. Since we now seek to use the remaining capacity of W minus Wn in an optimal way across items 1 to 3 and so on to n minus 1. When the nth item is too big, that is, W is less than Wn, then we must have OPT of NW equals to OPT of n minus 1 W. Otherwise, we get the optimal solution allowing all n requests. by taking the better of these two options, using the same line of argument for the subproblem for items among the set 1 to 3 until I, and the maximum allowed weight W gives us the following recurrence. 6.8. If W is less than Wi, then OBT of IW is equals to OBT of I minus 1 W. Otherwise, OBT of IW is equals to the maxima taken among OBT of I minus 1 W and Wi plus OBT of I minus 1 W minus Wi. As before, we want to decide an algorithm that builds up a table of all OBT of IW values while computing each of them at most once. Subset sum of NW. We have array M, which with index 0, 1, 2, 3 until N, and another dimension of index 0, 1, 2, 3 until W. Initialize M of 0W equals to 0 for each W equals to 0, 1, 2, 3 until capital W, where the capital W is the input of this subset sum. Now, after we initialized all of them from the row 0 and the column, all the columns to be 0, if the row is 0, then we do the following loop. For I equals to 1, 2, 3 until N, this is the outer levels of the loop, because there are two levels of a loop. This is for scanning for all rows. Now for the columns, with the inner loop, for little w equals to 0, 1, 2, 3 until capital W, we use the recurrence 6.8 to compute M of IW. And after we finish such two levels of a for loop for computing the recursion, we return M of NW, the rightmost and the bottommost element in the array. So if you see the figure 6.11, you can think of what we just said before. Using 6.8, one can immediately prove by induction that the returned value M of NW is the optimum solution value for the request 1, 2, 3 until N and available weight W. Analyzing the algorithm. Recall the tabular picture we considered in figure 6.5 associated with the weighted interval scheduling, where we also showed the way in which the array M for that algorithm was iteratively filled in. For the algorithm we've just designed, we can use a similar representation, but we need a two-dimensional table reflecting the two-dimensional array of subproblems that is being built up. Figure 6.11 shows the building up of subproblems. In this case, the value M of IW is computed from the two other values, M of I minus 1W and M of I minus 1 with the column W minus Wi. As an example of this algorithm executing, consider an instance with weight limit capital W equals to 6 and N equals to 3 items of size W1 equals to W2 equals to 2 and W3 equals to 3. We find that the optimum value OBT of 3, 6 equals to 5, which we get by using the third item and one of the first two items. Figure 6.12 illustrates the way the algorithm fills in the two-dimensional table of OBT values row by row. Next, we will worry about the running time of this algorithm. As before, in the case of weighted interval scheduling, we are building up a table of solutions M, and we compute each of the values M of IW in big O of 1 time using the previous values. Thus, the running time is proportional to the number of entries in the table. 6.9. The subset sum with input n and capital W algorithm correctly computes the optimal value of the problem and runs in big O of nW time. Note that this method is not as efficient as our dynamic program for the weighted interval scheduling problem. Indeed, its running time is not a polynomial function of n. Rather, it is a polynomial function of n and w, the largest integer involved in defining the problem. We call such algorithms pseudo-polynomial. Pseudo-polynomial algorithms can be reasonably efficient when the numbers of the set wi involved in the input are reasonably small. However, they become less practical as these numbers grow large. To recover an optimal set S of items, we can trace back through the array M by a procedure similar to those we developed in the previous sections. 6.10. Given a table M of the optimal values of the subproblems, the optimal set S can be found in big O of n time. Extension the knapsack problem. The knapsack problem is a bit more complex than the scheduling problem we discussed earlier. Consider a situation in which each item I has a non-negative weight wi as before, and also a distinct value vi. Our goal is now to find a subset S of maximum value summing for all vi with the summation summing over all index I in S, subjected to the restriction that the total weight of the set should not exceed capital W. That is, the summations of a wi summing for all index I in S is less than or equals to capital W. It is not hard to extend our dynamic programming algorithm to this more general problem. We use the analogous set of subproblems OBT of IW to denote the value of the optimal solution using a subset of the items among the set 1 to 3 until I and a maximum available weight W. Here the W is little w. We consider an optimal solution O and identify two cases depending on whether or not n is in O. If n is in O, then OPT of NW is equals to OPT of
not
n
in O,
minus 1.
then OPT of NW
is
equals to OPT
if
of
n is
n minus
not
1W.
in O. If n is in O, then OPT of NW is equals to Vn plus OPT of n minus 1 and capital W minus Wn. Using this line of argument for the subproblems implies the following analogy of 6.8. 6.11. If W is less than Wi, where the W is little w, then OPT of IW is equals to OPT of I minus 1W. Otherwise, OPT of IW is equals to the maxima taken among OPT of I minus 1W and VI plus OPT of I minus 1 and W minus WI. Using this recurrence, we can write down a completely analogous dynamic programming algorithm, and this implies the following fact. 6.12. The knapsack problem can be solved in big O of n times W time.